So this session contains talks about various features that we are developing into HDF5. The first talk is from Quincey Koziol, which is a project that I co-lead on developing the features to support experimental and observational data. And the next three talks are related to HDF in the cloud based on the HSDS server and two applications based on the HSDS. Okay, Quincey, if you're ready, you can share your screen and start the EOD.
Super. Thanks, Aaron. So this is a bit of a mouthful, but this is HDF5 features for managing experimental and observational data and superfacility capabilities. So lots of times I'll be talking about experimental and observational data as EOD. So you'll hear that a lot here too. So this project was initiated in response to many use cases that are coming up in science today with large experimental facilities that we show a bunch here that are mainly focused at light sources, but could relate to almost anything. Data gathering from a fusion experiment or a radio telescope, certainly not light in the same sense of, recording temperatures is not the same thing, but these ones are some examples of facilities that we were focused at for these projects. The National Center for Electron Microscopy is basically taking very high resolution microscope pictures and would really like to be able to handle additional capabilities or have additional capabilities in HDF5 in order to handle their requirements. I'll talk to all these guys, individual requirements in a single slide. The LCLS2 is a new facility that's coming online at the Stanford Linear Accelerator Center. And they're going to be, creating hundreds of gigabytes a second and would really like to move toward using HDF5 as the output from their experiments and their data gathering. Similarly, for the Advanced Light Source and Lawrence Berkeley National Laboratory, we're reaching some very high levels of bandwidth needed from this facility as well. And similar kinds of capabilities with some interesting twists as well from their facility. Is there a question? I can't tell.
No, I was just typing the.
Oh, sorry. Okay, thanks. Yeah, just pop in if there is a question. It's easier to talk and hear them that way. So this is a use case from the LCLS2 facility where they have light sources, detectors running on the left side over here, and they would really like to be able to create data locally, produce a set, one or more, of HDF5 files locally again, have data transfer nodes, these DTNs, on their facility at Stanford, watching those files that are created, and then anytime there's updates to those from the camera, the data recording, send it over the ESNet, the DOE's kind of global at this point, network capability, over to receivers at NERSC, so sending it across the bay, basically, to data transfer nodes that are set up running at NERSC, and then condensing those pieces of information back into HDF5 files and using them to guide visualization or input to machine learning or other simulations or archiving, any of these kinds of capabilities that are enabled by moving the data off of a very large science facility somewhere over to a supercomputing facility in a remote location. Similarly, the advanced light source examples, they'd love to have their data being gathered into what they called suitcases of HDF5 data and then transferred. In this case, it's across campus on the Lawrence Berkeley lab site, but then sent into the NERSC global file system to do analysis on the systems that are current, which are not Carver, Harper, and Edison anymore. We have Corey and the new one coming online, Pearl Nutter, by the end of the year or so. and then be able to access those, do metadata lookups through maybe a MongoDB that indexes the HDF5 data and pulls it off of tape and then feeds it to a user scientist. So these kinds of interesting, how do we get the data off of the science facility into HDF5, share it, look it up, and visualize it to produce science results, right? That's our end goal here. We're not interested in creating a file format for a file format. We really want to enable the scientists to do this discovery on their data. So boiling all these EOD use cases down and kind of picking the common ones, the ones that are most likely to pay off for not just these facilities, but many facilities across the country and internationally. We'd really like to have better support in HDF5 for sparse data. We need this remote streaming. You could see that in at least 2 of those use cases. Frequently, there's multiple cameras or multiple light sources or multiple data sources in some way, and multiple consumers of the data. That's really valuable. And particularly for the LCLS2 use cases, they produce records from their light source. The data records tend to have variable sized components. You could think of them as regions of interest that aren't square all the time, and sometimes the size varies as well. ALS would also like to see a sense of, well, I went in there and I tweaked the parameters on my microscope or on my light source, and now my data has a slightly different provenance. How can we show the changes in the data? So we can record those changes and also be able to understand, oh, these changed here. So how do we do some enabling of versioning control on HDF5 data? So reframing this back into HDF5, we'd really like to have a pair, in this case, of virtual file drivers, things that deal with bytes and offsets in the files, that split the data up into multiple files, and maybe could be stacked on top of this mirror VFD or a client server VFD to send data to a remote system. That's one set of capabilities. I'll talk to it. We need to enhance sparse data in HDF5. The H5 Prov, the provenance capturing, as well as this version controlling, both very valuable for the LS use cases. They also would like this metadata indexing, querying, so that they can do the lookup and pull the data back off of the tape system. And again, for Slack, they have existing data. They've been using a file format they call XTC. It's XTC2 now, but to create files for many years, for decades. And they'd love to have those files be accessed from HDF5 applications. They also have this variable length data storage requirement. And of course, we're dealing with very high bandwidth data, not just from them, but from other places. And we really need to enhance HDF5's capability for dealing with all that. So these are the kind of bullet points summary of what I'll talk through in a little bit more detail here. If you've got questions, please feel free to stop me and we can chat about any of them. So the splitter mirror combo, you can see this here in the diagram, is really the best. Locally at Slack, the HDF5 library is executing that top part of the diagram. And instead of just storing the file on the host file system, it passes through this splitter virtual file driver, and that sends data locally, so we don't lose it just in case the network goes down or something. But it also splits part of the data and sends it to this mirroring capability. So that capability, that VFD, takes those bytes, sends them to a remote host. In this case, we're targeting running the remote host on a NERSC data transfer node and receiving those and storing those there. Yes. John will be, we'll have more details about the virtual file driver later on as we get through these presentations today. So you'll see more details about the virtual file driver, but you can think of it as a very low-level pluggable interface for HDF5 that deals with bytes. Next piece of this, well, lots of these things, they have regions of interest that are sparse. They would really like to only store some of those frames or some of that data, not the entire set of blank data that doesn't have any science information, just these particular regions of interest in the sparse areas. So you can kind of work around this with HDF5 right now. If you use chunk data set and compression, it's a reasonable approach to trying to compensate for sparse data. You know, if there's a little bit of data in one chunk, it'll get stored. All the other chunks won't get instantiated. And you'll have a much better compression ratio and a much better overall data storage. But really, we could do better, right? What we'd like to do is do what we're calling sparse chunks. These are chunks that have metadata in them that says, hey, by the way, only these elements inside this chunk actually have data. So they actually are sort of a sparse representation within the chunk. And we can completely eliminate storing any of the other data in the chunk at all. And this nicely preserves the array abstraction. It provides all the space savings that we'd really like to have here. And we've prototype this out at kind of a high level, not necessarily down at the low level inside the library where it eventually will reside. And you can see very nice, of course, read and write speed ups and space compression. It's kind of a logical extrapolation. Is sometimes 5 to 10x faster I/O, and of course many times better space storage savings. So next piece, we'd like to actually determine when we change the knob on the light source on the microscope and figure out what's going on. So one of the aspects we've done here, and we'll talk more about the virtual object layer tomorrow, but it's a high level abstraction within HDF5. It doesn't deal with bytes and offsets. It deals with objects and operations on those. So create a data set or store some data elements, very high level at that level of things, understands the science concepts, the data model concepts, not just bytes. So what this vol connector does, this is a plugin that we've written to track which user, what application, what's the data that was written, timestamp, all these things. So it provides that provenance capture. It says at this point in time, somebody turned a knob, they stored some different data, and they updated it within the file. We'd like to see that get more productized and integrated further into production streams. So this would be very useful for identifying HDF5 usage and prefetch and other things that we can connect it to as we continue with this project. And sort of the flip side of that is well, the user turned the knob. We'd like to be able to roll back just to check to see if they did the right thing. Can we get back to our previous set of the data, the version before this one? So if we enhance the virtual file layer with a new driver, so we can track changes. This is very similar to version control and source code systems. This is very much like CVS or Subversion or Git for HDF5 files. We're not going to overwrite previous pieces of information, but we can indeed roll back to previous versions. And John will be talking, we'll have further presentations, more details about these guys. So I'm going to kind of touch base on this one lightly. We have lots of things in this talk, only a few minutes. So another capability we're very busy, right? Very interested in trying to help support this user community. A project called Mics. It's metadata indexing and querying for self-describing files. It's a mechanism for storing metadata and indexes around the data in an HDF5 file so that later on you can query those back and say, hey, what were all the data elements that fit this query, right? Suren and some of the research that he's been working on has been implementing these kind of indexes in order to do query support. And you can see there, it's crazy faster, right? 170,000 times faster to do a query with this kind of index compared to a more traditional database. So science data time to science, essentially, we can improve that quite a bit for the end result of a user kind of dialing through, where was the data I created, which patterns fit this query. So these last 3 bullets are encompassed within a project that's called the Lana Superfacility project. It's a joint effort between the Stanford Linear Accelerator and NERSC, and it covers 3 basic tasks for HDF5. There were several other tasks that were very valuable for superfacility efforts, but I'll just, of course, focus on the HDF5 ones. So there's 3 main goals here. We wanted to provide access to legacy, and as much as they're currently still being produced, they will be probably produced for quite a while longer, several more years at least. XTC2 files at SLAC, and we'd like to be able to open those files up to application and other users through different HDF5 APIs. There's a huge ecosystem of tools and visualization, cloud support, all kinds of interesting things you can do with HDF5, right? But the support for XTC2 is, of course, much more limited, right? It's SLAC users in a certain sense. If we could take those files that were created at SLAC and be able to access them through HDF5 without changing them in any way, we would open up the SLAC data files to a much, much broader community. And you could see from the slides earlier, we're streaming data across the bay. This is going to be a terabit connection, right? We need very high performance to handle stream data in HDF5. So some of the enhancements I'll talk about focus on that. And again, these regions of interest, they're sometimes irregular and they vary in size. We would really love to have better support for that in HDF5. So I'll talk a little bit about the hybrid chunks and the stream-focused chunk index. So XTC2 is awesome. It does the right thing. It has some very nice optimizations that have been worked on for many years that are focused in at a streaming level and are very tailored to that environment. They handle the SLAC light sources in really optimized ways. But still, we'd like to be able to open those up to a broader community. And we've done this by implementing this vol connector. And this is completely transparent. If you have an HDF5 application and you'd like to read an XTC2 file, the app doesn't even have to be rebuilt. It can be just change the environment variable. You choose to use a different vol connector and open the XTC2 file. Don't even have to recompile, don't have to rebuild, don't have to do anything. You just point your environment variable at the right vol connector and interpret the XTC2 files directly. And this is really the thing I want to emphasize. You can use HDF5 vol connectors, and I'll talk more about this tomorrow, access lots of different kinds of data through the HDF5 API. This framework allows any file, source, any source, not even files, to be piped in through the HDF5 API, and you could write an adapter. I'd really like to see more community contributions. We've done ones for obviously XTC2, the Audios BP format, NetCDF, traditional classic CDF format. All these are available and popular in science, but there's so many more. People could really jump in and write a vol connector that access data in any format that they find valuable to import into HDF5 applications. So moving on to the streaming API, we'd really like to see that performance improve. There's increasingly turning the knob up on the sample rate for these kind of light sources. And as part of that, we've been working on improvements to the streaming record appends and record reads inside HDF5. Here you can see these baseline performance numbers start off, thousands-ish milliseconds, hundreds to thousands-ish milliseconds once they scale out. And with these improvements we're working on, we're seeing 10 times better performance for streaming data and accessing it back later with read operations for fixed length data and even for variable length data, which is tough. The way HDF5 currently stores it, it's still seeing 2 or more times faster improvement in their performance for accessing that data again. We're going to do this probably. We're prototyping out some new cursor API routines that you can think about them in terms of a data set that's in a database, a table. So you create a cursor and then you kind of sequence through your table, right? So it's going to be similar in HDF5 data sets. We'll create a read point or a write point, and then you'll be able to say next, 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 next. And we'll amortize the setup and teardown that normally is associated with dataset read and dataset write operations. Some of it goes up into that cursor create, and then we can really optimize the actual next, 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 next IO operations. Finally, variable length storage in HDF5. We'd really like to, you could see from the previous slide that that's roughly 4 times slower to get to a variable length piece of data, a string, a simple record in HDF5. We'd really like to see that improve both in terms of access time and file size. It's not terribly efficient right now. It works just fine, but it could certainly improve. So currently these are implemented with what we call heaps in HDF5 files that store the variable length data elements. And then when you're appending, they use chunks to break up the data set into the individual pieces so you can sequence through them and append at the end, which is really the important part. But those, how do you find a chunk in HDF5 is you use a chunk index, but those are mainly focused at random access right now. We really like to see some way of unifying these data storage and then stream enabling the chunk indices. So as an example, this is sort of what, cartoon drawing of an HDF5 data set on the left that has fixed size records. And when you need to store variable sized data in a fixed sized place, well, you have to store it off to the side. And this object on the right-hand side is what a heap in HDF5. So when you store variable length information in HDF5, what you're actually storing is a pointer in the fixed size space, and that pointer goes into the heap at a certain offset and references the variable sized components. And so those can kind of point to locations in the heap. This doesn't look terrible right now, but if you throw a couple data sets at it and you read and update those data sets, not necessarily in the same order, you can get some horrible crosstalk in traffic and bad IO access patterns in the long run, ultimately. This next place is where we're going to go, right? And this is horrible. This is going to be impossible for you guys to read. I've got a very nice 40-page document that describes this and does everything. But there's 2 aspects I think are important. The first one is down here. Well, I can't even highlight correctly. The very bottom, you can see what amount to chunks. These leaf nodes, leaf node 0, 1, da, da, da. These are hybrid chunks. These have a little bit of metadata in them. All the fixed size data for that chunk that we previously would store only fixed size data inside the chunk. But now we're going to open that up to some hybrid unified chunk where all the variable length data that is appropriate for those records in that chunk is stored in unified mechanism inside the file. So whenever you need to access data in that chunk, you get the variable length data right away. So one IO call to pull in the whole chunk, and then you can access the fixed length data and the variable length data simultaneously from memory. So that's one solution that helps with the access times. Simultaneously, we can switch to this top component, the E+ array part, and that has what you can see between these leaf nodes with these little next pointers, right? And you're streaming through the leaf nodes at the very bottom, you never have to touch the index that's used for random access. You just get a pointer to the next hybrid chunk that's available for you to sequence through. So you never have to touch the random access data structure at the top. All you have to do is next, 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 constant time seeks streaming directly through the disk blocks to pull in the next hybrid chunk of data to read or write. And that should be a huge performance improvement for both lookups and storing these kinds of hybrid chunks in one single block instead of referenced off in more than one, at least two always. So these are the two main improvements we'd like to see, I'd like to see for the variable length data storage in HDF5. So all these are funded. I want to mention too that these are all funded by DOE projects currently, and we'd like to see as many of these efforts that we're currently doing get productized and delivered into locations in appropriate places, HDF5 or vol connectors, whatever, for science applications to use. And we're continuing to pursue funding to enable even more of these aspects. We couldn't get to all of the SLAC, ALS, NSEM, requirements in this go round, and not all of these guys got fully productized. So we'd like to continue to do this work and to deliver more capabilities to EOD applications and superfacility kinds of experiments. So any more questions, comments?
Thanks, Quincy. I addressed a few questions related to mix and other details. And we would like to, we would like to acknowledge this project had a HDF group as a partner, and John Mainzer played a major role in designing many of these features. So for the last minute preparation of the slides, we couldn't add all the details of the papers we have published and all that. Thank you. Okay.
Definitely.